The European Council for Nuclear Research has made a groundbreaking discovery that they are trying to keep hidden from the public. They recently discovered surprising results from the Large Hadron Collider, which suggests that extraterrestrial life may exist in other dimensions. The discovery has sparked a global conversation, with experts debating what it means for understanding the universe. Could this sensitive information indicate that we are on the verge of understanding phenomena once thought to be unattainable? At the forefront of scientific research, the European Council for Nuclear Research stands out for its pioneering work in particle physics. The renowned research center recently made a surprising announcement from the famous Large Hadron Collider, revealing a discovery that could revolutionize our understanding of the universe. Researchers stumbled upon a discovery that suggests the possibility of alien life in parallel dimensions. This provocative idea has sparked excitement and heated debate among scientific experts around the world. Since its founding in the mid-1950s, CERN has been a center for high-risk, high-reward experiments. It has consistently attracted attention for its scientific innovations, and has also drawn public outrage over potentially dangerous experiments that could create black holes, disrupt the fabric of reality, and cause other serious hazards. Among his most notable and discussed achievements is the construction of the Large Hadron Collider, the world's largest and most powerful particle accelerator. Operating since September 10, 2008, the Large Hadron Collider is the latest major addition to CERN's accelerator complex. It includes a loop of superconducting magnets about 16 miles long and a series of devices that increase the energy level of particles as they pass through the loop. The construction of this massive scientific machine cost more than $45 billion. However, many argue that the investment has paid off, as the Large Hadron Collider has led to some of the most important scientific discoveries of recent decades, including the discovery of the Higgs boson and many other particles previously unknown to science. CERN's Large Hadron Collider is a gigantic machine that is a marvel of modern science, capable of accelerating subatomic particles to speeds slightly slower than the speed of light. The particles spin more than 11,000 times per second along a path about 16 miles long, accelerated to incredible speeds by a series of incredibly powerful electromagnets. These magnets create a magnetic field inside the collider that is nearly 1,000 times stronger than the natural magnetic field surrounding the Earth. There are concerns that this strong magnetic field could potentially affect nearby electronics and the Earth's magnetic field itself. The goal is for the particles inside the Large Hadron Collider to collide head-on with each other once they reach a maximum speed close to the speed of light. These collisions release enormous amounts of energy and create bursts of new particles flying in all directions. Most of these particles last only a short time and disintegrate in fractions of a second. By changing the types of particles that collide, scientists can search for and discover previously unknown particles in the chaotic aftermath of these collisions. To capture and analyze the results of these particle collisions, the Large Hadron Collider is equipped with advanced detectors located around the collision site. These detectors collect vast amounts of data from each collision, recording everything precisely. The data collected is vast, accumulating quickly, and requires a lot of time and resources to organize. Each year, experiments at the Large Hadron Collider generate more than 15 petabytes of raw data. A major milestone was reached in 2017, when the Collider's tape library continuously stored more than 200 petabytes of data. To put this data size into context, think of a petabyte as the equivalent of about 250,000 movies. The scale of the data generated by the Large Hadron Collider is enormous, containing a wealth of information that holds clues to the mysteries of the universe. By carefully analyzing this data, researchers can peer deeper into the fabric of reality and test the limits of our understanding of physics and the universe. In the vast ocean of data collected by the Large Hadron Collider, scientists are meticulously searching for clues that could reveal new secrets of the universe. One particular area of their research is a unique type of subatomic particle known as a quark. Quarks are the building blocks of all matter and come in several types, or flavors, as physicists call them. Each quark behaves differently, but they are all important in forming the protons and neutrons that make up all the atoms around us. Some of these scents are incredibly unstable and quickly transform into other types of particles shortly after they are created. One such unstable quark is the beauty quark. Beauty quarks are known to have an unusually short lifespan of about 1.2 trillionths of a second. This unusual property of beauty quark decay has caught the attention of scientists. Generally, according to the standard model of particle physics, when beauty quarks decay, they are transformed into lighter particles called leptons under the influence of a force called the weak nuclear force. The expected result is that there is an equal chance of becoming one of the two types of leptons, electrons or muons. However, recent findings from the Large Hadron Collider have revealed something unexpected. Instead of decaying evenly between muons and electrons, beauty quarks decay into muons about 70% of the time. This significant departure from the expected 50-50 split suggests that something unusual is going on that cannot be fully explained by current physics theories. This anomaly has sparked intense interest and debate among physicists. The observed discrepancy suggests that a previously unknown particle could be influencing the decay process, or that it could be causing an entirely new type of physical phenomenon. Such a discovery would be groundbreaking and could mean that our current understanding of fundamental forces and particles may need to be revised. Researchers are now investigating these data in greater depth to confirm these results and fully understand their implications. If true, it could open a new era in physics, with the potential to discover new forces or particles that could fundamentally change our understanding of how the universe works. After a startling discovery, deeper secrets are being revealed, hinting at forces we've never seen before. The particle that could rewrite physics has been tentatively named Z'. The discovery of the particle carrying this new force could revolutionize our understanding of physics, potentially extending our current standard model, which describes the fundamental forces and particles that make up the universe. While this model has been remarkably successful in detailing the three fundamental forces, electromagnetism, the strong force, and the weak force, it still fails to account for gravity, which is thought to account for most of the mass of the universe, or for dark matter. The potential for new physics suggested by Z' comes from recent observations that contradict existing predictions. Given the wealth of data from experiments like the Large Hadron Collider, such anomalies are not unheard of. But one recent discovery has caught the attention of the scientific community. The results suggest the potential existence of particles that behave differently than we currently understand and interact in unexpected ways with known particles like electrons and muons. These new particles could hold the key to solving long-standing mysteries of the universe. For example, the discovery of a new fundamental force could shed light on the elusive nature of dark matter and shed more light on the role of the Higgs boson in the composition of the universe. More broadly, this could lead to a more complete and unified theory of physics, which has been a central goal of the field for more than a century. The implications of this discovery are profound, providing answers to complex questions that have puzzled scientists for decades. The proposed interactions of the Z' particle with other standard model particles are currently largely speculative, but the quest to understand them is an exciting prospect. It is similar to past major breakthroughs, but unique in that it would fill a gap in current theory that would represent a potential paradigm shift in physics. The excitement in the scientific community has been palpable as researchers around the world confirm the existence of Z' and study its implications. If confirmed, this discovery would not only redefine our fundamental understanding of particle physics, but also open the way to new technologies and understanding of the structure of the universe. Elon Musk emphasized that the European Nuclear Research Committee built the largest and most powerful particle collider, known as the Large Hadron Collider, over a period of 10 years, from 1998 to 2008. This monumental project was a collaborative effort of more than 10,000 scientists from over 100 countries and hundreds of universities, research institutes, and laboratories. The Large Hadron Collider is strategically located in a massive tunnel about 16 miles long, running under the French-Swiss border, about 574 feet below the Earth's surface near Geneva. The construction and operation of the Large Hadron Collider marked a major milestone in the field of particle physics. He first made headlines when he detected proton collisions at an unprecedented energy level of 3.5 TeV per beam, breaking the previous world record by a factor of 4. Subsequent improvements to the collider have enabled even higher energies to be achieved, up to 6.5 TeV per beam. These advances have made the Large Hadron Collider particularly adept at handling proton beam collisions, and also equipped to accelerate lead ion beams. The collider is not only designed to achieve high energies, It also plays a key role in scientific experiments. For about a month each year, the collider performs special collisions between protons and lead ions. This period is very important because scientists use it to test various theories in particle physics and study data to confirm or challenge existing models. One of the main goals of this experiment is to study the properties of the Higgs boson, an essential particle in field theory that explains why other fundamental particles are different.